Natural gas and petroleum gases often contain sour components, primarily hydrogen sulfide, H2S, and carbon dioxide, CO2. These gases are highly toxic and corrosive to equipment, making their removal essential for safety and infrastructure protection. Our project demonstrates the Amine Sweetening process, designed to remove these harmful impurities and recycle the amine solution for continuous reuse. Before we dive into the technical details of our model, let's look at the list of the equipment installed in the process. First, the inlet separator removes free liquids and solids from the raw gas. Next, the amine contactor chemically absorbs acid gases from the rising stream. Then, the outlet separator at the top prevents any amine liquid carryover from exiting with the treated gas. Right after that, the low-pressure flash tank safely releases entrained light hydrocarbon vapors from the rich solution. Following that, the rich amine pump handles fluid transport, supported by a dedicated bypass line for flow control and maintenance. To save energy, the lean/rich heat exchanger cross-heats the fluid streams. Beside it stands the regenerator tower, which thermally strips out the captured acid gases. At its base, the reboiler boils the liquid to generate stripping steam. Next, the storage tank serves as a buffer for the recycled solution. And finally, the water-cooled final cooler resets the amine to its ideal operating temperature. Now, let us follow the step-by-step fluid flow to see how these units work together. The process begins as sour gas, which contains H2S and CO2, passes through the inlet separator, where free liquids such as water and hydrocarbon condensates, as well as solid particles, are removed to protect downstream equipment and ensure efficient absorption. Then it enters the amine contactor, or absorber, a tall vertical pressure vessel whose function is to bring the sour gas into direct contact with the amine solution so that the acid gases are chemically absorbed and removed. The sour gas enters the contactor from the bottom and flows upward, while lean amine enters at the top of the tower and flows downward. The amine reacts with the acid gases and absorbs them from the gas stream. As the gas reaches the top, it enters an outlet separator to remove any amine that might have been carried over from the contactor. Once the amine has been separated, the gas is referred to as sweet gas. This is the opposite of sour gas, as it no longer contains H2S or CO2. This purified gas is now safe for transport and meets all environmental standards. Meanwhile, the amine solution exits from the bottom of the contactor as rich amine, now containing the absorbed acid gases. The rich amine then flows into a low-pressure flash tank, a vessel whose function is to drop the pressure so that light hydrocarbons trapped in the amine, such as methane, ethane, and propane, can escape before the solution enters the regenerator, protecting it from contamination. These recovered gases are typically sent to a fuel gas system or a flare. At this stage, the focus shifts from gas cleaning to amine regeneration. The goal is to strip the acid gases from the amine so it can be reused in the cycle. The rich amine in the flash tank, now separated from the light hydrocarbons, is moved by a transfer pump, whose function is to pressurize and push the rich amine solution forward through the system. This pump is equipped with a bypass line, which is essential for regulating the flow rate and allowing the system to continue operating during maintenance or pressure fluctuations. The pump sends the solution into the lean-rich heat exchanger. This is a critical energy-saving component. The hot lean amine returning from the regenerator transfers its heat to the cold rich amine. This efficiently warms the rich solution before it enters the desorber, while simultaneously cooling the lean stream to prepare it for the next stage of the cycle. Moving forward, the preheated rich amine enters the regenerator near the top. From the outside, the regenerator resembles the amine contactor, as they are both tall vertical towers. The rich amine enters below the reflux section, which is designed to capture any vaporized amine and return it to the process. The regenerator operates under high temperature and low pressure conditions. This environment is essential because it reverses the chemical reaction, allowing the acid gases to separate from the amine solution. Once the acid gases are removed, they exit through the top of the regenerator for disposal or sulfur recovery. As the rich amine flows downward, it contacts the rising steam that strips the H2S and CO2 away. At the base of the tower, the amine enters the reboiler. The reboiler is the heat source of the entire regeneration process. It heats the amine to its boiling point to generate the stripping steam. It is critical to drive 95% or more of the acid gases out of the solution before it reaches this stage. If too much H2S or CO2 remains, these gases become extremely corrosive under the high temperatures of the reboiler, potentially damaging the heating elements and the shell. The hot, regenerated lean amine returns to the heat exchanger to transfer its energy, then flows into a storage tank. Finally, a pump takes the lean amine from the tank and moves it through a trim cooler or final cooler. In this unit, the amine is cooled using cold water to reach the exact operating temperature required for the absorber. The cold water enters the exchanger from the bottom to ensure the shell is completely filled and to eliminate any air pockets. This bottom-to-top flow guarantees maximum contact between the water and the pipes, providing highly efficient cooling before the amine returns to the absorber to complete the closed-loop cycle. From the trim cooler, the amine is injected back into the top of the absorber column, where it is ready to scrub a new stream of sour gas. This continuous recirculation ensures that we achieve maximum gas purity with minimal chemical waste. And that is how the entire system works together to clean natural gas and reuse our resources. That's all for our project. Thank you for your time, and thank you for watching.